Hello everyone, welcome to PHARMAELITE. Today we are here with the next video from Boost Your Basic series on the topic of chemical kinetics. Now what is basically chemical kinetics? Chemical kinetics is the study of chemical reactions with respect to the reaction rate. We will hear this word very often in the whole lesson, that is reaction rate. Now what is all this in detail we will see as we move further. And when you study about reaction rate, it will be based upon the different variables, rearrangement of atoms, the number of factors like temperature, concentration of reactant, catalyst, all this will affect the reaction rate. And to express this rate of reaction, we have a mathematical expression which is called as rate law. Also, this is an important term. In the whole chapter, you will study about rate law, rate of reaction, reaction rate, half-life, shelf life, all these concepts come under chemical kinetics. So let us begin. Now basically, what is rate of reaction? We'll understand it through a simple example. Rate of reaction basically tells us as what speed the reaction occurs, that is how fast or how slow the reaction is going to occur. Let us take a simple example of a reactant A getting converted to product B. As the concentration of reactant A decreases, the appearance of B will start. That is, we know at the beginning of a reaction, there is whole of a reactant A, and as time passes, the amount of A will decrease and amount of B, that is appearance of B, will increase. And at the end of reaction, you will have maximum amount of product, whereas negligible amount of reactant left. Thus, the rate of reaction is defined as the change in concentration of any reactant or product per unit time. That is, either you describe the rate with respect to the reactant or with respect to the product. For a given reaction, the rate of reaction can be equals to the rate of disappearance of A, or which is equal to the rate of appearance of B. That is minus of dA by dt. Why this is minus? Because it is disappearance of A, that is amount of A is decreasing. So it is minus of dA by dt, or rate can be with respect to B, that is product, plus dB by dt. It is positive sign because the amount of product formed is increasing in its concentration with respect to time. And this A and B in the square bracket is the concentration which is in moles per liter. And there can be different units which can be used to describe this reaction rates, which could be moles per liter per second, that is mole, liter inverse, second inverse. What is in the denominator will be represented in this form, that is liter inverse and second inverse. Or moles per liter per minute, that is mole liter inverse minute inverse. And mole liter R, that is mole liter inverse R inverse. These are the different forms in which you can express the reaction rates. Now, what is rate law? This is another term which will frequently come across, rate law. Now, the rate of reaction is directly proportional to the concentration of reactant, each concentration being raised to some power. That is, the rate is proportional to concentration A raised to N, or rate is equals to K A raised to N. This is how you can express a rate law. That is, a reaction is expressed mathematically in the form of rate law, wherein you express the concentration with respect to some power. Let us take example of this reaction, reactant 2A plus B giving you products. So you can describe the reaction rate with respect to A or with respect to B. You can vary the concentration of one, whereas other is kept constant. Thus, the rate of reaction can be expressed as rate is equals to K A raised to M and B raised to N. Now, this is the rate law expression. That is, K is the constant, that is the constant which is used here in place because you're replacing the proportionality sign. You don't have to go in the details of derivation part of it. Just the expression is important. And what is A and B? These are the concentrations. And M and N, these are the exponents or powers of the concentration which are used in rate law. And it is usually a small whole number like 1, 2, or 3, or it can also be fraction. And K is the proportionality constant, also called as rate constant for the particular reaction. And this M plus N or M and N are exponents or powers of concentration which are used in rate law expression. And this rate law expression, you cannot just simply form it on theoretical grounds by looking at the reaction on mass and number of moles. It has to be found out experimentally. That is, based upon just looking at the given reaction or the amount of product. You cannot say there are 2 moles of this and 1 mole of this, so I'll make this expression accordingly. It has to be experimentally found. That is, rate law expression has to be determined by experimental grounds. These are some of the examples you can see here. N2O5, that is 2 molecules of N2O5 giving us 4 NO2 plus O2. In this reaction, the rate law expression, rate will be equals to K, that is proportionality constant, into concentration of reactant. See, you cannot rate law, so you cannot say there are 2 moles of this, so you are putting 2 moles here. Rate law, it is determined experimentally. So when H2 plus I2 react to form 2HI, here there are 2 reactants, so the rate law will be dependent upon concentration of both H2 as well as I2. In the next case, when there is NO2, 2 moles of it giving 2 NO plus O2, again in this case the rate law is dependent upon concentration of NO2 raised to the power 2. Because this is experimentally determined, you cannot just enter the values by balancing the chemical reaction. Then the next example is NO plus H2 giving N2 plus H2. Again here both the reactants are involved in determining the rate law expression, and H2 and NO raised to the power 2. This all the rate law expressions have to be derived experimentally. Now what do you mean by order of reaction? This is another term which we are using very often in chemical kinetics. Order is the sum of powers of concentration of reactants in the rate law expression, and that particular sum of powers is called as order of reaction. We have just now seen an example, same is taken here. A raised to M and B raised to L. So A is raised to M, the power of A is N and for B is N. So the sum of it, that is M plus N, will give us the order of reaction. And the order of reaction can also be defined with respect to a single reactant. That is, with respect to A, the order is N. With respect to B, it is N. And overall, it is M plus N. And this value, that the sum of the powers, that is order, can range from 1 to 3, or it can also be a fraction. That is, M plus N, if it is giving you value 1, it is a first order reaction. When M plus N gives you value 2, it is a second order reaction. And when it is 3, it is a third order reaction. Again, you can see here from the rate law expression, you can find the order. You just cannot look at the reaction. See, first from the reaction, you cannot predict the rate law. It has to be found out experimentally. Similarly, you cannot find the order based on the reaction. You need the rate law expression to get the order. So from the rate law expression here, there is nothing means it is raised to 1. So order of reaction is first order. Now here it is 1 plus 1, 2. In case of NO2, it is raised to 2. So it's a second order reaction. In this case, H2 raised to 1 and NO raised to 2. That is 1 plus 2 will give a third order reaction. And again here, chloroform and chlorine, this is 1 ½ Order can also be a fraction or a whole number. So it is 1 plus half, that is 1 ½ This is how you get the order of a reaction by adding the powers of reactants. Now first let us look at zero order reaction. A zero order reaction is the one whose rate is independent of concentration. Very, very important point to remember. Which reaction whose rate is independent of concentration. Now let us look at the example for a zero order reaction. Here a reactant A getting converted to products. At initial concentration, the amount of product is 0. And you have a reactant A. As time passes, there is appearance of product X. So the amount of reactant left will be A minus X. In that case, the rate of reaction is minus of dA by dt, which is equals to Ka raised to 0. So now you can see anything raised to 0 is 1. So it is minus of dA by dt is equals to Ka raised to 0 multiplied by 1, you can say, because this term, we don't have to go into entire derivation part of it. Just remember the final expression. What you get is X is equals to K not T. So in this case, you can see that the order is independent of, the rate of reaction is independent of concentration, that is zero order. where K0 is the rate constant for zero order and the unit of it is concentration per unit time. Therefore, for zero order reaction will be concentration, that is mole meter inverse time will be time inverse, that is concentration per unit time. And now where you can find the zero order reaction, the applications are very important. One thing is you have to know the units. You should know that its rate is independent of concentration and the examples. Now what are the examples? Controlled release drug delivery systems follow zero order kinetics. You may be given example and whether it follows zero order or not. You should know if it is controlled release, yes, it will follow zero order. Osmotic drug delivery systems, that is all osmotic deliveries, osmotic pumps, they will follow zero order kinetics. Then matrix tablets with low solubility drug, implantable depot formulations, transdermal preparations, suspensions follow zero order kinetics. Another typical example is photolysis of cephaloxime. Then decoloration of sulfur drugs. And another drugs which follow zero order kinetics are warfarin, alcohol, tolbutamide, theophylline, and phenetol. Remember the examples of the drugs which follow zero order kinetics. You can get a direct question asking which of the following drugs follows zero order kinetics or which does not follow zero order kinetics. Now let us look at first order reaction. For a first order reaction, the rate of reaction is directly proportional to the concentration of reactant. In zero order, the rate was independent of concentration, whereas in first order, the rate is directly proportional to the concentration of reactant. That is, dx by dt rate is proportional to k into A minus x. And upon integration and solving, you also get this in the log form. That is 2.303 by t log of A upon A minus x. That is log of initial upon final concentration. And if you are finding out the expression at two different time points and having two different amounts decomposed, that is x1 and x2 at t1 and t2, you can modify this equation as k, that is rate is equals to 2.303 upon t2 minus t1 into log of A minus x1 upon A by x2, A minus x2. That is, these are two different amounts at two different time intervals from the start of it. Example for a first order reaction could be decomposition of N2O5 in CCl4, that is nitrogen pentoxide and carbon tetrachloride. This decomposes to give oxygen gas is an example of a first order reaction. Just you need to know the example, that is more than enough rather than going all the details of it. Another where you can see the first order kinetics is sustained release, matrix diffusion and controlled release, matrix dissolution, controlled release. All these will be following first order kinetics. And examples of drugs are salicylates, cisplatin, fluoxetine and omeprazole. Also, what are the units for first order? First order reaction, the units are time inverse. So as the rate constant, here what you are asked is rate constant is independent of concentration. So its units will be time inverse. That is, you can write it as second inverse, R inverse, because the rate constant, that is K, is independent of the concentration. Before we move further, do subscribe to our YouTube channel and make sure you press the bell icon so that you get a reminder when we post a video. We also have a free WhatsApp group where we are posting daily MCQs for GPAT, NIPER and other entrance exams, pharma related job openings and other related latest happenings. If you wish to get added to our group, please drop a message on below mentioned numbers. We will add you to our group. Now these are the plots of the rate law expression for zero order, first order and second order. If you plot a graph of concentration versus time, you get intercept as K0 and the slope will give you minus K value. Also, if you plot it for first order natural log of A versus time, you get a slope as minus K, and for second order, you get slope with a positive value. You can similarly plot a graph with log values. If you plot in first order, if you plot a graph of log of R0, that is initial upon final concentration versus time, for a logarithmic plot, you will get a straight line passing through origin and it will have a slope value of K by 2.303. These are the plots, but for the rate law expressions, you can also plot it with log values. Another important thing which you need to remember is the parameters, the half-life, what you are getting, the intercept and the slope. Here you can see when you plot concentration versus time, you get the value of slope. If you plot log versus time, you get it as k by 2.303. And if you are plotting it as 1 by a minus x versus time, you get slope value k. Also, the half-life expressions are important. That is, for zero order, the half-life, that is T half, will be a upon 2k. For first order, it is 0.693 by k. And for second order, it is 1 upon a into k. We'll look further in detail about half-life. First, let us look at units for an order of reactions. If it is a zero order reaction, the units are mole, liter, inverse, second inverse. This table is very, very important. You can get a direct question to identify the unit of a reaction, or you may be given a short MCQ to solve, based on which you can get the answer if you know the units and order of reaction. So first order, it is time inverse because it is independent of concentration. And for second order, it is liter, mole inverse, time inverse. Here the L is missing. Liter, mole inverse, time inverse. So second inverse, this is second order reaction. Remember the values for rate constant. Sorry, the units for rate constant based upon the order of reaction. Now, what is half-life? You must have heard about the word half-life. It is the time which is required for the concentration of a reactant to decrease to half of its initial value. That is, you have, say, X amount of a compound or a drug. The time which is required for it to reduce to X by 2, that is 50%, reduce half, is called as half-life, which is represented as T half or T 0.5. This is how you can remember the formulas. You can get a direct question asking the half-life of first order or second order, or you may be given some value, substitute and solve it directly. Provided you know the formula, you can solve it. For zero order, T half is R0 upon 2K. This is the, so here there is a concentration term, so its half-life is dependent on concentration. For first order, you can see this T half is 0.693 upon K. Here there is no concentration term involved. So the half-life of a first order reaction is independent of its concentration. So in case of first order, the half-life is independent of its concentration, whereas for rate, it is zero order. We have seen in the first slide, right? For rate, it is a zero order reaction whose rate is independent of concentration, whereas for half-life, it is first order, which is independent of its concentration. For second order, the half-life is 1 by K upon R0. And to find the nth order, that is, if you're not given the order of reaction, you can use this formula. Basically, the first three are more than enough if you remember them. Now let us look at what is called as shelf life. Remember, shelf life and half-life are two different things. Don't get confused. Both are not the same. It is two different things. Shelf life is the one during which a medicinal product is predicted to remain fit for its intended use under specified conditions of storage. That is, when you have a medical product and you keep it for storage, how long is it medically fit, or how long can it use for its medical use, is dependent upon its shelf life. Now, shelf life is a time for the potency of a drug to be reduced to 90%. That is, when you manufacture a drug, or it is when it is newly made or manufactured and brought out in the market, its potency is 100%. But as time progresses, a potency of a drug at a certain point, it will start decreasing. So the time at which the potency of a drug is reduced to be at 90%, that is, the drug is now 90% potent instead of 100, that is 10% of its potency is lost. And the time during which this potency reaches to 90% is called as shelf life of a drug, and it is expressed as T90. Again, you just need to know the formulas. For a zero order reaction, the shelf life, that is T90, can be 0.1 into R0 upon K. It is dependent upon the concentration. And for first order, it is 0.105 by K. Its shelf life is independent of concentration. So it is just very easy to remember the formulas, and then you can solve the question. There is another thing in chemical kinetics called as Arrhenius equation. You must have heard the concept of Arrhenius. So it is found that as the temperature increases, the rate of reaction increases. There are different variables which will affect the rate of reaction, that is concentration, temperature, and other factors. So when you increase the temperature, say these are the molecules which are here. As you increase the temperature, they get more energy. And as they get energy, their movement becomes vigorous. So with vigorous movement, the molecules will start colliding with each other. And this energy is called as activation energy. And Arrhenius equation is something which relates energy, temperature, and the rate of reaction. As the temperature is increased, the molecules will have more and more energy greater than that of activation energy, and it produces productive collisions. And this will increase the rate of your reaction. It also helps in predicting the shelf life of a drug product. So Arrhenius was the one who suggested a relationship between the rate constant K and the temperature of a reaction. So this is the expression Ka e raised to minus Ea upon RT. Here K is the rate constant, A is the one which is experimentally determined by Arrhenius, and Ea is the activation energy, R is the universal gas constant, and T is the temperature in Kelvin. This Arrhenius equation will give the relationship between how your rate constant for a reaction and its temperature are correlated, and how much of the energy is required for the molecules to be produce productive collisions. So when you find out these values, you can get the rate constant, that is K, if you know A, E, and activation energy and temperature. Also in the log form, it is log K is equals to minus of Ea by 2.303 RT plus log of A. Also, it can be found at two different reaction rates. It's two different rate constants, K1 and K2 at respective temperatures of T1 and T2. Then the expression changes to this form. I'm sure you must have definitely seen this formula earlier and solved some numericals in your lower classes based upon the Arrhenius equation and the reactions occurring at two different temperatures to find out the rate constant of a particular reaction. Now let us look at some MCQs which can come. The rate constant for a zero order reaction has the units dash. Second inverse, mole, liter inverse, second inverse, liter square, mole raised to minus 2, second raised to minus 1, liter mole inverse, second inverse. To solve this question, basically you need to know what are the order of reactions and their units. So this table will help us reach to the answer as we have seen previously. For zero order, it is mole, liter inverse, second inverse. For first order, it is second inverse. And for second order, it is liter mole inverse, second inverse. Remember, the L is not printed here. So the correct answer in this case is mole, liter inverse, second inverse, because we are asked for zero order. So the option B. Next question. The half-life of which reaction is independent of concentration of reactant? We are asked half-life which is independent of concentration. Also, there is another wherein the rate is independent of concentration. That is a different question. So here, when you say half-life, the options is zero order, first order, second order, and all of the above. Now to know this, again you need to know the half-life formula. For zero order, it was T half is equals to R naught upon 2K. R naught is the concentration term, so it is dependent on concentration. Here it is first order, T half is equals to 0.693 by K. So it is independent of concentration because you cannot see any concentration term. In second order, again you can see it is T half is equals to 1 by R naught upon 1 by R naught into K. So it is again a concentration term which is involved. So, and this is for the nth order. So you can see here from all of the above, the one which is independent of concentration is a first order one. That is, its half-life does not depend upon the concentration. So the correct answer here in this case is first order reaction whose rate of reaction and in which the concentration and half-life are not dependent upon each other. That is, if you go to plot a graph, you will get a straight line. That is, its half-life does not depend upon the concentration. When you plot rate versus concentration, this will be for a zero order reaction. When you plot rate versus concentration. And for half-life, it is first order reaction. Next question. When the initial concentration of a reaction is doubled, The half-life period of a zero order reaction is dash. Halved, doubled, tripled, and remains unchanged. Again, you need to know the half-life formula. We are given zero order reaction. So the formula for half-life of a zero order reaction. I hope you all remember the formula for half-life of a zero order reaction. It was dependent upon the concentration. So it is R naught upon 2K. So when you say the concentration of the reactant is doubled, obviously the half-life is directly proportional to the concentration. So the half-life will also be doubled. So the correct answer in this case is option B. That is, the half-life is also doubled when you double the concentration for a zero order reaction. Whereas if it was first order or second order reaction, the answer would have changed. Thank you everyone for watching the video. Stay tuned, more videos are coming up soon.